19th lecture being delivered on 21st, and the topic is complete response of electrical circuits. Before I take up examples, as you see, most of this theory I am doing through examples, and before I take specific examples I want to introduce a function called a step function. Have I done so earlier? No. And first I would introduce the unit step function. A unit step function is usually denoted by u of t. U for unit, t for time. It's a function of time, and a unit step function is 0 for t less than equal to less than 0, and at t equal to 0 it suddenly rises to a value of 1 and then stays constant for all times to come. This is the plot of u of t versus t. This is the unit step function. Well, as you see, if you switch on a battery V to a circuit, some circuit capital N, at t equal to 0, then what you are applying here is a step function of magnitude capital V. Is that clear? And this is why the step function, the terminology, is to be introduced at this point. That is, when you switch on a battery to a two-terminal circuit, what you are precisely applying is a step function of magnitude V. In other words, what you are applying is V times u of t. All right? What you are applying to this is V times u of t. Now, and the corresponding response, suppose I want the current I, is called the step response of the circuit. If capital V was unity, 1 volt, then you say it is the unit step response of the circuit. So this term step response is sometimes used to indicate what we have essentially been finding out when we switch on a battery to an electrical circuit. All right, this term shall now be used repeatedly. So I thought I must introduce this at this point. Last time, under complete response, we had considered a first order circuit to which a battery was introduced, switched on or switched off. We also saw a sinusoidal source being switched on to a first order circuit. Today we consider second order circuits. As you know, second order circuits must have two energy storage elements. It can be either two capacitors, or it can be two inductors, or a combination of the two, that is one inductor and one capacitor. If it is more than one element of the same kind, that is two inductors for example, they should be non-trivially connected. If they are trivially connected, then it becomes a first order circuit. So this must be remembered. If there are two different kinds of elements, one inductor and one capacitor, then there is no problem. You connect them trivially or non-trivially, they are storage of energy of different kinds. One stores what is similar to kinetic energy, and the other stores what is similar to potential energy. Who stores potential energy? The capacitor, and the inductor stores kinetic energy. Or you say one stores in the electric field, the other stores in the magnetic field. All right. So in a second order circuit, as you know, first thing is there must be two energy storage elements, which, if of the same kind, must be non-trivially connected. For example, this circuit, here the two capacitors C1 and C2 are non-trivially connected. You cannot combine them into one. So this is truly a second order circuit. On the other hand, if you have something like this, well, obviously this is a first order circuit. All right, this is a first order circuit. So two energy storage elements are needed. If of the same type, they must be non-trivially connected. A second order circuit is described by a second order differential equation. second order differential equation, and a second order circuit shall have two roots of the characteristic equation. All right. For example, you can have a second order circuit like this. This is a second order circuit, but when you are determining the current response to an excitation from here, all right, it becomes a first order circuit. Is that clear? If there is a voltage source here, all right, and you want to find out the current here, okay, in this circuit, then the response that you get essentially is that of a first order circuit. Why? Because for a voltage source, whatever you connect here, it doesn't matter. All right. So you must also see how the source is connected. A truly second order circuit is one in which the natural response is determined by two distinct frequencies, and therefore the characteristic equation of the circuit must have two roots, which may be distinct, may not be distinct, which may also be coincident, but two roots. Well, the simplest example is if a step voltage VUT is applied to a series RLC circuit. Let us say this switch is closed at t equal to 0, and we have a resistance, inductance and a capacitance R, L and C, and the problem is to find the current I. All right. Obviously, what we are applying to this circuit is a step of magnitude capital V, and if we assume that initially this circuit is de-energized or relaxed, then obviously I of 0 minus the current through the inductor, that is equal to 0, equal to I of 0 plus. This is one of the initial conditions, and the other initial condition is that Vc of 0 minus is equal to 0 is equal to Vc of 0 plus. These are the two initial conditions, and the natural response of the circuit, because it is a current, shall be determined by the zeros of the impedance function, that is R plus SL plus 1 over SC, and as you know, we can write this as S squared LC plus SCR. I am repeating this again and again so that it gets imprinted in your mind. And the style of writing is that we take the coefficient in the numerator and denominator both to be unity, highest power coefficient, and therefore we shall get L times, have I made a mistake? This is okay, S squared plus S R by L plus 1 over LC, and here we shall get simply S. So the pole zero diagram is that there are two zeros which are the solutions of this quadratic equation, and a pole at the origin, that is at S equal to 0. So the natural response of the circuit, that is INT, would have two exponential components, and these components shall have the frequencies given by S squared plus SR by L plus 1 over LC equal to 0, which means that S12 shall be equal to minus R by 2L plus minus square root of R squared by 4L squared minus 1 over LC. And depending on the sign of this, S12 can be real, negative, distinct. If R squared by 4L squared is greater than 1 by LC, they would be real, negative, coincident. If these two are equal, and they would be complex if R squared by 4L squared is less than 1 by LC. All right. So there are three distinct cases, and depending on what the cases are, the solutions for the natural response shall also be different. For example, for the first case in which the roots are real, negative and distinct, the natural response shall be A1 e to the minus S1t plus A2 e to the minus S2t, where S1 and S2 are, yes, okay. Is it minus S1? You recall we wrote S12 equal to minus R by 2L plus minus square root of R squared by 4L squared minus 1 over L. It should be plus S1, all right. Don't allow me to make a mistake. S1 and S2 themselves are negative. So it would be A1 e to the S1t, A2 e to the S2t. On the other hand, if the roots are coincident, that is if S1 equal to S2 equal to minus R by 2L, the discriminant is equal to 0, then my current response, natural response, shall be A1 plus A2t e to the power S1t. Third case, if S1 and S2 are complex, S12 equal to, let us say, minus alpha plus minus j beta, that is if the discriminant is negative, then my natural response would be of the form A e to the minus alpha t, a damping coefficient, multiplied by sine of beta t plus theta, where beta is called the damped frequency of oscillation. The damped these terms we have introduced, and alpha is called the damping coefficient. All right. Now, if you go back to the circuit, what was the circuit? Have I taken it too fast? Is it okay? All right. What was the circuit? The circuit was that I had a battery of voltage V switched on at t equal to 0 to this circuit R, L and C. And we said we have found out the natural response INT. What about the forced response? The forced response for the current obviously is equal to 0, because at infinite amount of time the capacitor, when the battery, to the battery the capacitor acts as opaque. It does not allow any current, and therefore IF of t is equal to 0, and therefore the total solution is equal to IN of t, and the two constants A1, A2 or A and theta, A1, A2 in the first two cases, A and theta in the third case when the roots are complex, shall be determined from the initial conditions that I of 0 plus equal to 0 and V sub C 0 plus is also equal to 0. The two initial conditions shall determine this. Let us take a variation of this example and try to solve it. Okay, there is one small point, that V sub C 0 plus equal to 0, this does not enter into the solution or evaluation of the constants directly. What it does is that this is 0, I 0 plus equal to 0, so the drop across resistance is 0, and therefore L di dt at t equal to 0 plus becomes equal to V. This is how this initial condition comes into the picture. This also I have discussed earlier. So in a sense, so far it has been a repetition. Now let us look at a slightly tricky situation, that we have a 1 volt battery, 1 volt battery, and there is a switch here which is opened at t equal to 0. This switch is shunted by a capacitor C, all right. Then we have an inductance L and a resistance R, L equal to 1 Henry and R equal to 1 ohm. It is this current that we are interested in, current I for t greater than equal to 0 plus. You see, for t less than 0, when the switch is there, obviously the current shall be established at I of 0 minus shall be equal to 1 ampere, all right. I of 0 minus shall be established at 1 ampere, and what is L di dt at 0 minus? It is 0. all right. When now the inductor, the current through the inductor cannot change suddenly, and therefore when this switch is opened and the capacitor is put in this circuit, the current must remain at 1 ampere. And what about this voltage, the voltage across the inductor? It will change. Let us see if it changes. You see, the capacitor cannot change its voltage suddenly. Alright, so the capacitor remains at 0 volts. The resistance, the current through the resistance is 1 ampere, and therefore this is 1 volt. So what is the drop across the inductance? It must be 0. So depending on the condition of the circuit, the initial conditions may be different. In other words, this is also true for L di dt 0 plus. Not only here the current cannot change, the voltage also cannot change, because we have made it a constrained situation, that is, the capacitor has been suddenly switched in, and the current, since the current cannot change, the total drop occurs across resistance. All right. So you must look at the problem to be able to determine the initial conditions. Now at t greater than 0, at t greater than 0 plus, all right, our circuit is this: 1 volt, then we have a capacitor C. The capacitor is given as 5 by 16 farad. All right, I have chosen it for reasons that you will see in a moment. We have a 1 ohm and 1 Henry inductor. This becomes the circuit, and therefore to determine the current I, in the circuit, we should determine the impedance looking into the circuit. All right, Z of S. Then we shall be able to find out the steady state response and the natural response. All right. So we look at the circuit and we see that Z of S, the impedance is given by 1 ohm resistance plus SL, L is 1 plus S, plus 1 over SC, that is 16 by 5S, and therefore this is 5S squared plus 5S plus 16, which I can write as S squared plus S plus 16 by 5 divided by S. All right, and I determine the zeros of this, that is S squared plus S plus 16 by 5 equal to 0, gives us the roots as S12 equal to minus half plus minus square root of 1/4 minus 16 by 5. No, have I made a mistake? 5 by 16. No, I want it the other way around. I want this to be 5 by 16. So what should I change? Pardon me, I changed the capacitor. Okay. Pardon me. I want to keep life simple, so I'll make this 16 by 5. Okay. Will you make this change? 16 by 5 farad. Then my coefficient here becomes 5 by 16s. So does the whole thing change? Oh dear. All right, my choice is bad, but anyway, do the roots still come real? Oh, they don't come real. Okay, I goofed up. Pardon me? Let's not cook the example now. The point that I was making is, we'll leave it in the middle of it. We'll take some other fortunate example. Well, the point that I was making is, if S12 is obtained, doesn't matter whether they are complex or real, it doesn't matter. Suppose they are complex, as it happens in this case, all right, then my equation would be a e to the power minus alpha t sine of omega t plus theta equal, this is the I of t, and This is the In of t, the natural response. And in common with the previous example, this must also be the total response of the circuit, because the forced response, it is after all a DC, a battery, forced response is 0, and from this you can find out A and theta by equating the initial current to 0, A sin theta equal to 0, and the initial di dt also equal to 0. All right, the two equations will then determine the constants. All right, we take a slightly different example now, where a sinusoidal generator, a voltage generator, sinusoidal, is switched to a series RLC circuit. Let us see what happens. A series RLC circuit, and I hope I have taken the values now not to end up in a mess. R equal to 12 ohms, L equal to 2 Henry, and C equal to 0.1 farad. All right, and the switch is put on at t equal to 0. Now no longer have we applied a step voltage, because V of t now is sinusoidal, 20 cosine 5 of 5 times t. This is the voltage. Okay. In other words, here we shall have to solve for both In of t and If of t. All right. As far as If is concerned, all that I have to do is to find out Z of the impedance between, what I want to find is the current, and therefore I find the impedance between these 2 points, Z of J, what is omega? 5, isn't that right? Cosine of 5t, so omega is 5. Z of J5, this would be 12 plus J omega L, so J omega is 5 and L is 2, so J10, then plus 1 over J omega, that is 5, C is 0.1, and therefore this is 12 plus J10 minus J2, that means 12 plus J8. All right. This is my impedance, and therefore, and what is my voltage phasor? Voltage phasor is 20 divided by root 2. This must be remembered, angle 0, and therefore the forced current phasor If shall be equal to the voltage, which is 20 divided by root 2 0 degree divided by 12 plus J8, all right, which I can write as 20 divided by root 2 square root of 144 plus 64. How much is that? 208, and the angle would be minus tan inverse, yes, 2 by 3. Agreed? Minus tan inverse 2 by 3, because this is the angle of the denominator. When it goes to the numerator, it becomes negative. All right. So this I can write as 20. Well, you see that this is 16 multiplied by 13. I hope I am right. 4, 3, yeah, okay, 16, and square root of 16 is 4. So I can write this is 5 by root 13, 1 over root 2 minus tan inverse 2 by 3. Can we write If of t now? Yes, it would be 5 by root 13. You must multiply this by root 2. Okay, that's why I didn't absorb root 2 in this quantity. Then cosine of, yes, 5t minus tan inverse 2 by 3. This is the forced response. Now to determine the natural response, I must find Z of S and its zeros. Okay. Without writing Z of S, I know that the natural response shall be determined by S12, where S12 is minus R by 2L plus minus square root of r squared by 4l squared. This result I already know. I don't have to write this again and again. And in this particular case, if you take the values of R and L, R is 12 ohms and L is 2 Henry. So 2 times 2, which means that this is equal to 3. 12 by 4 is 3. So plus minus square root of 9 R squared by 4L squared minus 1 over LC, that is 1 over 2 times 0.1, and that would be 5, and therefore this is minus 3 plus minus square root of 4, which is equal to 2, and therefore the roots are minus 1 and minus 5, which means that In of t shall be equal to A1 e to the minus t plus A2 e to the minus 5t. Is it okay? Right. Therefore, my total current response I of t shall be A1 e to the minus t plus A2 e to the minus 5t, then plus 5 by root 13 cosine of 5t minus tan inverse 2 by 3. The problem that remains is to find out A1 and A2. Now what are the initial conditions? I of 0 shall be equal to 0 because why? Because the inductor current cannot change instantaneously, and therefore 0 shall be equal to A1 plus A2 plus 5 by root 13 cosine of minus tan inverse 2 by 3. Now cosine of a negative angle is the same as cosine of the positive angle, so it is cosine of tan inverse 2 by 3, and without consulting a table you know how to find out cosine of tan inverse. Tan inverse means this is 2 and this is 3, right? And therefore cosine of this angle, this will be, therefore this would be equal to 3 by under root 13, which means that 0 shall be equal to A1 plus A2 plus 15 by 13, and therefore A1 plus A2 shall be equal to minus 15 by 13. Without consulting the table, it is possible to write it in this form, alright. And what is the other condition? Other condition is di dt, L di dt at t equal to 0 plus should be equal to why is that? Let's look at our circuit. This is the point that I wish to emphasize, that every circuit has its special initial condition. Okay, this is the circuit. Okay, Vc 0 minus is 0, so Vc 0 plus must be 0. Now the current at 0 minus is also 0, so the drop in R and the drop in C both are 0. Therefore L di dt at t equal to 0 plus must be equal to the voltage of the source, which is equal to, so it's no longer 0. You have to look at the conditions of the circuit to determine the initial conditions, and therefore my expression for I of t, which was A1 e to the minus t plus A2 e to the minus 5t plus what was it, 5 by 13 cosine of 5t minus tan inverse 2 by 3, not root 3, 5 by root 13. So if I differentiate this and put t equal to 0, the second condition becomes minus A1 minus 5A2, alright, plus 5 by square root 13. If you differentiate a cosine, it becomes a minus sine, and therefore 5 that comes from cosine 5t, then a minus sine sine 5 t equal to 0 shall be 0 minus tan inverse 2 by 3. I must distinguish, this is the bracket. Alright, now see how this simplifies. This should be equal to how much? 20 by L, and what was L? 2, and therefore 10. Alright, the initial conditions must be identified properly and must be utilized properly, and therefore what I get is minus A1 minus 5A2 plus 25 divided by square root 13. Now what is minus minus, so that will make plus, sine of 2 by root 13. Alright, sine of this would be 2 by root 13, and this would be equal to 10. The other condition, as you know, was found out as A1 plus A2 was equal to how much? Minus 15 by 13. I have a doubt. No, 15 by 30. So these are the two equations that you have to solve now to find out A1 and A2. Alright, so the style of working for finding the complete response is you must find both the natural response and also the forced response. For the forced response would be similar to the forcing function. If it is DC, then the forced response will also be a DC. If it is an exponential function, the forced response will also be the same exponential function. If it is a sinusoidal function, then it will be sinusoidal. And if it is sinusoidal, then we don't have to work in terms of time domain, we can work in terms of the phasors, and that is a great simplification. On the other hand, the natural response, if you have to find a current, then you find z of s and take its zeros. If you have to find the voltage, then you take z of s but take the poles. Alright, so the natural response will be determined by either the poles or the zeros depending on what you want. Alright, in this context, a term which is sometimes used for determining the characteristics of electrical circuits is the so-called pulse response. We have already said what is a step response. A step response is when a battery, a unit step response would be one in which a battery of 1 volt is switched on at t equal to 0. A pulse is one which is non-zero for a duration, for a certain duration, and then it becomes again 0. For example, if this is a voltage pulse, then this voltage is typically, let us say, is at capital V between 0 and capital T, that is its duration is capital T. Alright, this is called a pulse, and in the laboratory you shall get so-called pulse generators, where you get not just one pulse, you get a repetitive pulse. Why do you require a repetitive pulse? Because if you wish to see the response of an electrical circuit to such an excitation and you want to see it on the oscilloscope, then you have to repeat this. So you get a repetitive pulse generator. But if you look at it, this voltage pulse can be written in terms of two step functions. One is capital VU of t, which is a step which goes on indefinitely, minus another step occurring at capital T. Alright, so minus V U, it does not occur at t equal to 0, it occurs at t equal to capital T, so t minus capital T. Is that okay? This voltage pulse can be represented by the difference between two steps, each of amplitude V, but the second one occurring at a later instant, that is capital T. You see, if you add the red curve with the pink curve, then this is what you get precisely. Alright. Now you also know superposition, and therefore if a voltage can be broken up into two voltages, obviously the response, suppose you apply this to to an electrical circuit and you want to find the current IT, then the response would be I1t minus I2t, where I1t is the response to VUT and I2t is the response to VUT minus capital T. Alright. You see, the only difference between these two is that one is delayed, that is small t is replaced by T minus cap T, and therefore I2t must be equal to I1t minus capital T, right? And this is a way to determine the response of an electrical circuit to a pulse voltage like this. Let us take an example. Let us say a pulsed voltage of this nomenclature, that is the height is capital V, height is capital V and the duration is 0 to capital T. Let us say such a voltage is applied to at t equal to 0 to a series RC circuit, a first order circuit, to keep things simple, and we wish to find the current I. So what we do is we first find the current I1t, we first find the current to a step of magnitude capital V, and you know what this current shall be. We know that this would be V by R, and then what? This current, if I simply apply a voltage like this, then the initial current would be V by R, because initially the voltage across C is 0, alright, and therefore it will be V by R. Then it would decay with time according to e to the minus t by RC. Alright, let us call it as V by R. Let us call this time constant, because I have used capital T here, let us call it as tau, t by tau. And this response obviously is valid for the time interval between 0 and capital T, because at capital T something else comes into the picture. So the total response therefore shall be I1t minus I1 of t minus capital T. Now here a certain discipline has to be imposed on ourselves, namely that this I1 of t is true only for t greater than equal to 0, and therefore I multiply this by u of t. What is a u of t? Unit step function. It is 1 for t greater than equal to 0 and it is 0 for t less than 0. Therefore this is the correct solution. We did not include a u of t because it was implied in the context, but now we have to discipline ourselves, because I1 of t minus t starts functioning only at small t equal to capital T. So I cannot combine the two unless I use this function. Therefore what I get is V by R e to the minus t by tau u of t minus V by R e to the minus, instead of t we shall have t minus capital T divided by tau u of t minus capital T. Is this clear? Is this point clear? I have founded the two responses independently. I could not write without u of t, because then the second term would have affected the response even for small t less than capital T. Isn't that right? And this is why I had to write t minus capital T. This function is unity only when small t is greater than or equal to capital T. Otherwise it is 0. Now if I sketch this, if I sketch the current waveform, my current waveform I of t is V by R e to the minus t by tau u of t minus V by R e to the minus t minus capital T by tau u of t minus capital T. Now if the versus t, if the second term was not there, then the current would have started falling from V by R, okay, it would have started falling like this. But as soon as capital T, the time is capital T, it is joined by a negative current, and this negative current starts from minus V by R and goes to 0 like this. Okay, this negative term goes to 0 like this. So what do you think will happen at t equal to capital T? The current shall suddenly come down by how much? This minus this. In other words, this much. It will come down by this much, so it will go somewhat like this. And then what will happen? As t tends to infinity, it will go towards 0. As t tends to infinity, both terms go towards 0. So this will be the current response. And you see there is a jump. In the current response, di dt has a jump here. Di dt is discontinuous at this point, at the point t equal to capital T. Alright. Suppose we wanted to find out, is this point clear? The pulse response. Basically, the current is continuous, but di dt is discontinuous. Suppose instead of the current, we wanted to find out the voltage V sub C. What would have happened? V sub C, if only the first term was there, that is, if only there was a step excitation, then what would happen to this voltage? This voltage would start from 0 and go to capital V at infinite amount of time. All right. In other words, without writing the equations, V sub C of t versus t, and let us say this is capital V, then the voltage across the capacitor would have risen like this and would have gone to infinity, would have gone to capital V at infinite amount of time. Now at this point, when the time is capital T, what happens? It is joined by another term which is negative, but it starts from 0 and then goes negative, goes to minus V, and therefore what will happen to the capacitor voltage? It will gradually decrease and go to 0 at t equal to infinity. So this will be the capacitor voltage. Is this okay? So you know how to determine the pulse response. We have introduced two terms. One is step response, which you have understood. It's simply switching on a battery, step response. We have also found out pulse response, which is equivalent to switching on a battery and then another battery in the opposite polarity at some time later. Now there is also a third term called impulse response, which I want you to understand carefully. Impulse response. But first let us define what an impulse is. Okay. Suppose I have a voltage V of t which is a pulse like this. It's a pulse like this, 0 for t less than 0, this is t, 0 to capital T, and let us say this height is capital V. The area under the pulse area is equal to capital V times capital T. Alright. Now suppose I keep the area constant, allow capital T to decrease, then naturally when capital T has become T1, the voltage will become V1, such that this area remains a constant. Area is a constant, V1 T1. What happens when capital T tends to 0? Capital V shall go to infinity, capital V shall go to infinity. This limiting case which cannot be generated in the laboratory. You cannot generate an infinite voltage, all right. You cannot generate a voltage which stays only for 0 amount of time, capital T tends to 0, but nevertheless it is a physical concept which is extremely useful in the analysis of signals and systems. This is true, this analysis is true whether it is a mechanical system or a chemical system or whatever it is, because most of them shall be simulated by means of an electrical circuit, and therefore the concept of an impulse is extremely important. An impulse can be thought of as the limiting case of a pulse whose width tends to 0 and height tends to infinity in such a manner that the area is constant. And in this context we define a quantity known as unit impulse. A unit impulse delta t is represented by an arrow here, arrow occurring at t equal to 0, just an arrow. We cannot represent infinite amplitude on a finite two-dimensional plane, and therefore we simply represent an arrow and we denote the area under the impulse. Well, if you want to distinguish, make it a solid arrow like this. Let us represent the axis by means of an open arrow whose back is open. Here the back is closed. The area under the curve or under the pulse, whose limiting case is the impulse, is written here, is written by the side of the arrow. This simply means that integral delta t, delta tau d tau, it exists only at t equal to 0, and therefore we go from 0 minus to 0 plus is equal to 1. This is what it is. If I have an impulse whose area is capital A, as in the previous voltage pulse was, then an impulse of strength capital A shall be denoted by A delta t, and it shall be represented by an arrow, solid arrow, with its strength or area. This area is also called the strength of the impulse, written by its side, which means that if you integrate this from 0 minus to 0 plus, that is over basically an infinitesimally small interval, then this would be simply equal to capital T. There must be a dt here, all right, which means that if the impulse, instead of occurring at t equal to 0, suppose it occurs at t equal to capital T, its strength is capital A t, all right, then this impulse representation would be A times delta t minus capital T. The delta function or the unit impulse function exists only when its argument is equal to 0, that is, it occurs at t equal to capital T. Now if capital T is greater than 0 and you integrate this impulse, let us say from minus infinity to 0, what would be the value? 0, because it has not included capital T. The integral from t minus to t plus shall be simply equal to A. This is not a conventional function in the functional sense of the term. This is a concocted function. Nevertheless, it has great importance in theoretical physics and in engineering, and this function was introduced by the famous physicist P.A.M. Dirac, and therefore this is also known as Dirac's delta function, all right. Now suppose I have an RC circuit. Now come to the plane. Suppose I have, let us say, an RL circuit, and I have a voltage which is a unit impulse, which is an impulse of strength capital A, all right. I wish to find out the response of this. This is switched on at t equal to 0, and I wish to find out the current I. Now comes contradictions to our hypothesis, which we have been working so far with. I of 0 minus is 0. I of 0 plus should have been 0. Isn't that right? Because an inductor cannot change its energy instantaneously. But this is a calamity situation, a crisis situation. You see, if you are standing at a slope and the slope is sufficiently low, well, you can resist the force of gravity. But you cannot obviously stand when the slope is very large. It is like a piece of ice coming down from a hill and you are sitting at the bottom of the hill. You can stop it, but when it's an avalanche you cannot, and therefore you are carried along. This is an avalanche situation. An infinite amount of voltage is applied over an infinitesimally small amount of time. The inductor has no other way but to accept an energy. Alright, this is a crisis situation. It does not obey the ordinary laws that we have so far. This is not equal to 0. And to find out I of 0 plus, what we argue is the following, that I of 0 plus cannot be infinity, because we are giving a voltage which exists only for infinitesimal amount of time. It may be infinitely large, but the current cannot go to infinity. Current must be finite. If the current is finite, then obviously the drop in R shall also be finite, and therefore the A delta T, the voltage source, must be fully dropped across L, and therefore the current I 0 plus must be 1 over L integral V dt, which is A delta T dt from 0 minus to 0 plus, and you see this is simply A by L. Let us call this I 0. Is the point clear? Pardon me? Say that again. It contradicts our common sense, but as I said, it's a calamity situation. There is a voltage source which goes to infinity but stays only for 0 amount of time, infinitesimally small amount of time. So the effect is at t equal to 0 plus, t greater than equal to 0 plus, the voltage source is gone. Now what would be its effect left in this circuit? Obviously the effect cannot be infinite current. It must be a finite current. If it is a finite current, then the drop across R shall be small compared to the drop across L, because L is multiplied by di dt, and di dt is infinitely large. There is no current, suddenly a current is established, and therefore L di dt must be equal to A delta t, because the current, the drop across R is finite. Any infinite drop obviously shall swamp the finite drop, and therefore I of 0 plus shall be L di dt is equal to A delta t, and if you integrate this equation, this is what you get, and the integral of delta t dt is unity, and therefore the I of 0 plus shall be I 0. So after the impulse has gone away, that is at t greater than equal to 0 plus, the inductor sees that it has accumulated an energy of half L I 0 squared, and this becomes a short circuit then. A delta t is 0, and therefore the natural response will come into effect. I of t will be equal to I 0 e to the power minus R t by L. Is that okay? And this is called the impulse response of the circuit. So we have introduced today 3 terms: step response, pulse response, and impulse response. Next time we will look at the impulse response from a different point of view, as the limiting case of a pulse response, and we will see that we get the same result. All right.